All right, so here we are on question 4. This time, if you read through the null and alternative hypotheses in the question, it says we want those who were treated with the magnets to have a greater mean reduction in pain. Well, the mean magnet treatment group is the group 1, so we want their mean to be greater than, so that leads us to choosing C. All right, let's just trust our calculator and dive into our 2 sample t-test, and we'll type in all the data, which is 0.56. 1.03, 21, 0.54, 1.56, and 21. And we are doing a greater than test. And calculate. So it looks like our test statistic is 0.049, which is very small. Sorry, to 2 decimal places, so 0.05. Always got to read the blue text. Oh my goodness. Alright, 1 minute. Let me just double check what I typed in. I must have made a mistake. 0.58. And there's the mistake. Alright, just that small difference. So check your answers carefully. Alright, there we go. That's a different t-value. To 2 decimal places, that's actually going to round up to 0.10. Alright, and the p-value is 0.461 to 3 decimal places. And because that p-value is very large, especially compared to the 0.01 significance level, we are not going to be able to reject because there is not sufficient evidence. Our result is not rare enough to think that we are not lucky, the null must be false. Alright, now this one is really interesting. I'll be honest, this is actually my second take on this question because my whole entire life teaching statistics, I've only ever used this confidence interval comparison when the alternative was strictly not equal to. And so what happens is when our alternative is one-sided, our confidence interval is no longer 1 minus alpha. It's actually 1 minus 2 alpha, essentially because we're only doing one side. Now instead of both sides, that whole 1-2 switch somehow affects our confidence interval as well. So now when I go to do I'm still going to rely on the calculator, when I do my 2 sample t interval and I use all the same data from before, instead of saying I want a 99% confidence level compared to the 1%, which is what I would have done, again, if the alternative was involving inequality, what I'm going to do instead is I'm going to use a 98% because this is one-sided. And let's see what it gives me. It gives me, I said this is my second attempt, but I haven't made sure that anything else ugly doesn't happen, but I'm pretty sure it doesn't. Yay, there we go. All right. And so once again, that confidence interval does contain 0, which means it's plausible that there is no difference between these two. All right, so it appears that magnets are not effective because 0 is in the interval. All right, that sounds right. Is it a valid argument that magnets might appear to be effective if the sample sizes are larger? No, because the magnets already appear to be defective. That's not true. No, because increasing the sample size will increase the p-value. That's not true. This is a really interestingly worded question. All right, well, let's just say one thing. Changing your sample size doesn't increase the effectiveness of your, whatever you're testing at all. The more you sample, it won't make something more effective or less effective. But the more you sample, remember that n lives inside of the denominator. And so the more you sample with n will make any difference you see look more significant in its p-value. So I think that's what we're going for here. All right, but in other words, the magnets being effective or not is the truth or not. But if you do sample more people, that difference will be accentuated more if you observe it. All right, and once again, here we go through example 5. Let's go through this one. Does giving candy result in greater tips? So if we do give no candy or 2 candies, that's population 2. So does population 2 get greater tips because they give the candies? And that's going to be one-sided. So does population 2 get greater tips? There it is. We're going to run through the test statistic, again, by relying on our calculator. We might be able to just do this in StatCrunch, but we'll use our calculator because that's what we get on our exams anyways. So I'm going to input the data. X bar is 18.09. Standard deviation is 1.32. Sample size is 24. The other average is 20.92, 2.52, and the sample size is once again 24. This time, again, it's this direction, which is one-sided, so if we see a confidence interval, we're going to watch out for that. Let me see if I can zoom in on this a little bit. Looks like it zoomed out somehow. There we go. So we get a t-value to 2 decimal places of negative 4.87. And the associated p-value is very small. It's essentially 0 because there are 4 leading zeros, so to 3 decimal places, that's just all 0. And so that means we definitely have enough evidence to reject, because if my p-value is 0, I got a ultra-rare result if the null was true. If the null was true, getting my result is theoretically impossible, so the null must not be true. There must be evidence that giving candies results in greater tips. So there is sufficient evidence because I got such a rare result. All right, once again, we're going to construct the confidence interval. And when we go to the 2 sample t interval, everything is all well and good. The data's already been imported. But this time, again, what was our confidence level before? It was 0.01. So again, if the alternative was strictly not equal to, we would use 99 or 1 minus alpha. But when it's one-sided, it's 1 minus alpha times 2, or 1 minus 0.02 instead of 0.01. We double that alpha for a one-sided confidence interval. And here we go. We get negative 4.24 to 2 decimal places, 25 to 2 decimal places, and negative 1.41. All right, and does it support? Yes, it does, because it contains only negative values. And why does that make sense? Because if we have only negative values via subtraction, then the second number must have been bigger, or in other words, the average amount of tips from people who gave candies must be larger. That's why the subtraction came out negative 98%. Well, not necessarily came out negative, but 98% of the time, or rather, with 98% confidence, that's the way you say confidence intervals, you don't say percentages. With 98% confidence, we can be sure that the mean tips for candies is larger than the mean tips for no candies. All right, so if you're a server in a restaurant, statistics just helped you get some more money.